maybe we can get some. Yeah, sure. All right, welcome back. It's my great pleasure to introduce Dr. Jason Xu. So Jason is a professor in statistics at Duke, and I've known Jason for quite a few years. I always admire Jason's work. Sometimes I think Jason is very similar to Ken, or even Ken plus Mark. So he marks the chart. He's like a master of stochastic processes, infectious disease, and optimization, and now Bayesian statistics. So, and also I always enjoy sitting in Jason's talk. Always I can learn something. Very, very great speaker. So I definitely look forward to the same today. Yeah. Okay, Jason.
Thank you so much for the kind introduction, Hua. I think he's got it backwards, though. I've learned more from the people in this room than they will from me. And I will say a master of infectious disease might be a little more evil than I am. But let me begin by talking a little bit about my introduction to Ken before introducing my own talk. And indeed, I used to work a lot on stochastic processes, inference for stochastic processes. That's what I was doing my thesis on. A lot of related to kind of what Mark Suchard was talking about. And I proposed to work on that with Ken. And he said, this sounds great. And I was so elated to hear back from him because, you know, of course, a lot of that work was also influenced by his work in applied probability. And then when I got to UCLA, Ken absolutely had other plans. So this was 2016. I started my postdoc, and you might know Ken's book on majorization-minimization, he literally wrote the book on what I'll talk about, just came out. And so all Ken wanted to talk about was MM. And so I hadn't heard of MM really. I'd kind of, seen it here and there. And I think, since then, really my own career branched out, and I was introduced to so much. Today, I chose to focus on this topic, even though recently I've been giving a lot of talks on stochastic epidemic models, because it really is a new direction that has led to even more directions, as you'll see over the course of this talk. And all of this perspective was really opened up just working with those brief but transformative years with Ken closely during my postdoc. So it's a very fun time. And of course, throughout this talk, you'll see that all of these ideas were influenced not only by Ken, but by this community that Ken has introduced me to, many of the members of which are in the audience. So without further ado, I'll actually introduce my talk. I will be talking about MM algorithms, majorization-minimization. And in particular today, I'll try to give an overview, focus kind of on the simplicity behind this principle to design effective algorithms, and focus on a particular setting on a new class of penalties that allow us to do constrained optimization in a broad variety of settings. Okay. So, as many of you know, it's very common for statistical tasks to be cast as some kind of optimization problem. So the Bayesians in the room, there's also connections there. We'll have a little bit in the end. But it's canonical now to minimize some measure of fit to the data, but also have some kind of penalty that puts some regularizing structure so that we also don't overfit the data or to overcome challenges such as high dimensionality. And so as an example, just because this is one of the most sort of common use cases, I'm going to motivate today's talks, beginning with the example of sparse regression. Okay, so in this case, you've seen a lot of this in the previous talks already. But when we look for something like sparse structure in a solution, let's say a regression coefficient, it might be very difficult from an optimization perspective to find the exact solution under that sparsity constraint. That's sort of the L0 problem, which is in fact known to be NP hard by mathematicians and computer scientists. So it's very popular to consider sort of these approximations or relaxations of such difficult problems. And in this example of sparse regression, one of the most prevalent, seriously tens of thousands of papers that Ginevra said here too, is to use something called the lasso. And the lasso is the L1 or convex relaxation problem, trying to approximate that original sparse regression problem, right? So here you have some kind of measure of fit to the data, a likelihood, and the parameter you're interested in is denoted by beta. But rather than just maximize the likelihood or minimize the negative here, you also want to impose that regularization or penalty term, which is denoted here. And so in this case, I would like beta to have a small L0 norm, but instead I'm indirectly imposing that via regularizing its L1 norm. Okay? That's the idea behind lasso. Many of you are familiar with this. And as we've also seen in multiple of these talks, whether it's in the case of something like graph-based learning or something like trend filtering, these relaxations unfortunately do introduce some bias to our inference, right? So by shrinking the whole coefficient vector, we are biasing all those estimates towards zero. And in doing so, also, when you're trying to simultaneously do estimation and selection, we might introduce a lot of spurious selectors or false positives. So there's a huge literature on this. I'm just trying to do a little bit of justice. There's all sorts of other shrinkage penalties. These ones might be folded concave penalties that might not be convex, but they're also going to suffer somewhat at a high level from the same effects of global shrinkage. And in general, when we are solving this by proxy via, for instance, shrinkage, there's often a gap between that relaxation and the original desired structure we want to impose. Okay? So just as a motivation. And so one of these ideas that Ken sort of introduced me is to instead try to use something a little more directly incorporating that original constraint. And we've been calling this distance to set penalties, but the overall intuition is quite simple. If I can write down a very general constraint somehow as a set in the space I'm working in, then what I'd like to do, if I want to enforce that constraint, is to minimize the distance between my estimate beta and that set, right? So why is this? Well, if my constraint is satisfied, that translates to this estimate beta lying in that set. And if I'm in a set, then the distance from me to that set is 0. On the other hand, if I'm really violating this constraint, if I'm far away from the structure we want to impose, then the distance is going to be larger. So if I'm penalizing by that distance, I'm sort of paying a price the further I am from the structure I want. So here's a little picture. We see that if I want the distance from X to the set, another way to express, just write this mathematically, is the distance between that point and the closest point in that set, which I'm going to denote the projection onto that set C, right? So if this was my beta, then this point, which lies in the set but is closest, is the projection. And these penalties have been used a lot in optimization. They go back to at least the 40s and have a lot of nice properties. So not only are they going to give us a nice penalty framework, but the idea is that we're going to rely on projection. And fortunately, many useful projections for sets that come up all the time in statistics and constrained learning are things that we can manage computationally. So we've mentioned that this sparse problem is hard and we can't get over it completely. But if we're going to use a constraint-based approach with projections, then if I need to project a vector onto the sparsity set, it's really simple. I simply take all but the largest number of desired entries and set them to 0. Right? So retain the largest in absolute value entries. And if you want to get into slightly more complicated examples, if I want to do low rank constraints, I can do something similar by thresholding the singular value decomposition. And there's all sorts of other examples, whether it's some kind of shape constraints, order constraints. There's a lot of, in many of these cases, some smart people have already given us tools to compute such projections. So why do these distance penalties sort of mesh well with MM, right? So the penalized objective here, we're again compromising between the data fit and the penalty to the constraint, or in this case, we can write it with multiple constraints. Now we have these kinds of tuning parameters in front of the constraints, kind of like the lambda that you see in other formulations. But there is a little bit of a difference, which I'll emphasize later. The nice thing here is that we already see that in theory, if I let this parameter get even bigger and bigger, it's simply enforcing the constraint exactly more and more. Now, in contrast with something like lasso, we all know we have to tune lambda. If I let lambda get bigger and bigger, I'm not just getting closer and closer to the solution, I'm getting closer and closer to 0, which is actually going to be a big problem. Now, to bring this closer to the MM paradigm, we're going to use another observation that was pioneered by Ken as well as 2 others in this room, Eric G. and Wadzo, which is to say that it might actually be useful to further introduce another inequality on this nice distance object. If I have the distance squared between a point and a set, that's going to always be less than or equal to the distance, or the distance between beta and the projection of any other point. And so I wish I had that picture still here, but if the distance is defined to be the distance between beta and its closest point, then the projection of any other point has to be at least as far. So this is a pretty trivial inequality itself, but it will have a lot of useful consequences. It will allow us to build nice iterative algorithms when I choose this any other point to be some current iterate. Okay, and we'll see how that works soon. Now, to bring this into the MM perspective, again, many people in the audience here know about MM, but I'll still give a little introduction. And when this was introduced to me, like I said, it was a revelation. The idea here is it's not just one algorithm, but it's more of a recipe that allows us to transfer difficult optimization problems, maybe they're non-smooth, in this case non-convex, maybe both, instead to a sequence of more manageable, simple problems via what we're going to call surrogates. And if we can, let's say in the case of minimization, sequentially minimize those simpler problems instead, we'll still get to the original answer we desired. Like I said, originally I came to Cannes thinking I'd work on things like EM algorithms for these difficult stochastic processes. And in fact, EM, which is much more widely known to almost any statistician in a PhD program, is just a special case of MM, right? In fact, we have a difficult problem because of missing data. And instead, we're going to iteratively optimize a simpler objective at each stage. And that happens to be the expectation of the complete data. All right, so this iteration where we make this surrogate the expectation and then we maximize it is actually a special case of MM, which we'll see. So MM algorithms sort of generalize this geometry and operate on broader classes of problems. So not only did I build on the work of Eric and Hua in investigating these directions, but I think I stole these slides from Eric right here. So this is a little illustration of the simple geometry behind MM. Let's pretend that this black curve is very difficult to optimize. At a current iterate, I'm going to exhibit a surrogate function, find its minimum, which might be really easy. That gives me my next step. I'll again exhibit a surrogate function, minimize that, et cetera, and you see that you climb down that hill or uphill in maximization. So again, we can imagine that you can recreate this geometry without relying on something like EM where you need missing data. You just need to sort of allow that picture to go through. And what are the conditions behind this picture? Oscar nicely mentioned this in the last talk, but these surrogate functions just need to satisfy two simple conditions. They should be tangent at the current iterate. So on all of these pictures, it kind of was tangent right here. And then also, as we've seen in these pictures, they should be dominating or lying above the original difficult objective function. Okay? That defines this iteration of creating such a valid surrogate and then minimizing the surrogate. And then you can actually prove why this will decrease your original objective, and then in particular converge to a local optimum just in one line of proofs, right? And so many of you might have seen this. In fact, when I came here to do a postdoc, I was like, Ken, if this is all there is behind MM, I'm doing a postdoc because I want a job. Like this is just not enough substance. But then, I read the whole book and there's so much more to it. It really is an art. But really you can convince yourself that these two conditions substitute here and here. And that immediately shows why doing this iteration at the endpoints of this inequality does decrease, in this case, your original objective. Okay. So how do these distance penalties play? We've been calling these things proximal distance algorithms, and this was pioneered by Ken with one of his former students, Kevin Keyes. These surrogate functions will be whatever your objective originally was, plus this distance to set penalty, but now we're putting in that current iterate xk here, right? And we call it proximal distance algorithms just because if I look at this problem, it kind of looks like f plus this envelope. And formally, the next step is given by what's called the proximal mapping on this, which kind of represents an average or a compromise between minimizing this and kind of hewing closer to the argument here, in this case, the projected point. So I wanted to give a little bit of an overview where we've used this. Sort of one of my first forays was in applying to generalized linear model regression. So Ken had worked on some nice problems in genomics where they used things like iterative hard thresholding with projections. And it worked really well in the linear case. But in these nonlinear cases, when you move from linear regression to something more general, it seemed that you didn't want to discard more of the information from the gradients and the approximate Hessians. So we'll see that later. But again, many of you might be familiar with these models. A generalized linear model basically takes something like the linear regression relationship, but allows there to be a nonlinear possibly function that links this onto into some other exponential family distribution. Right? And so instead of least squares, we end up maximizing a different always concave function that's related to the likelihood under that link function. So just as an example, I don't know why this is broken. This is equation 1, you might guess. Under this example, if I choose some of these terms to be just the squared function, then we can recover linear regression as a special case. But there are many, many other examples, right? So logistic regression being one of the most prominent, but Poisson regression, any kind of exponential family you can imagine for the data. So these also have a lot of nice properties. And in this case, let's just see how it would look if we applied such an MM algorithm with these distance penalties, right? Because the objective is already nice, because the loss is nice, we're only going to motivate the penalty here. So if we want to incorporate some kind of constraint on the coefficient vector under this generalized linear model regression, I'm going to now make this substitution like I mentioned. And in doing so, because the likelihood was already nice and smooth, I can get the gradient and in fact a second differential readily. So I can use simple updates such as Newton type algorithms. Okay. And there's some other nice computational properties I'll show after this image of the algorithm. You could imagine that what it ends up looking like is something that just looks like a Newton step. In fact, this Hessian will actually be easier to compute than the general second order terms we would use. And then there's a simple backtracking step to ensure that everything is pointing the right way. So this is actually a really easy algorithm to code is the point. And we'll see that it was meant to be quite general. All we need to do is, again, write down any kind of constraint. If we can write it as a set and we can project onto that set, we're good to go to use quite familiar algorithm. And so there's a couple other nice computational points in the case of GLMs. In particular, when you have the canonical link, we have some nice properties of exponential families so that we can basically get the expected information. The expected information is going to be the right thing to put in for that second differential term. So not only going to be easier to compute, but it allows us to ensure that this term's always positive semi-definite, which could be a headache otherwise. This other contribution that comes from the distance penalties, it kind of adds to this term right here. And that actually has a nice computational effect. It kind of allows us to protect against ill conditioning because it's adding a multiple of the diagonal automatically. And then we have some nice things like the descent property just owing to the fact that it's an MM algorithm. This is also amenable to acceleration, but I don't want to dwell on that today. So just some quick results in some settings from that first paper. In the case of sparse regression, and in this case, we're looking at both the logistic and Poisson links for generalized linear models. We compared this to those folded concave penalties, which are already going to do a little better than lasso. And at least in this setting, again, it's not a panacea, but in the sort of low signal to noise ratio settings, our method is actually the MM here tends to do a lot better in terms of the mean squared error. Right. So again, there's in these kinds of applications, it depends on the regime, the signal to noise ratio, but in many such cases, we're doing a lot better. And of course, the algorithm is it's very flexible. So these MCP and SCAD in this case are catered to sparse regression, but we can kind of run that same general algorithm on many kinds of constrained problems for regression. And I actually didn't plot lasso here because it was actually kind of just not even within the scale of the axis. It had a lot worse error in this example. We also see that it does very nice support recovery for those coefficients in terms of selecting the true coefficients and not putting as much bias as those other competitors. So I don't want to dwell on too many simulation results in this talk in general. I just want to kind of present them and get on to the main ideas. But what's important is, like I said, this is not just for sparsity. So on that same algorithm, if I put in a different constraint in matrix regression, and this is also inspired by one of Hua's papers, we can now use that truncated SVD to do a projection onto the low rank set, right? So if we wanted to look for a low rank matrix signal, just as an illustration, this is a rank 2 image right here. And you can't just impose a sparsity constraint like a simple L1 constraint on that whole matrix. It'll kind of give you a bunch of garbage noise. What does make sense is to try to get at the low rank structure, but maybe the analog to lasso here would be something called the nuclear norm penalty, right? That's a convex relaxation of the low rank structure. And it does right, it does okay. But as I try to kind of tune lambda here, even when I'm tuning it well, there's still some fuzziness in this reconstruction on this simple problem. Whereas in this distance penalty, first of all, I can put in a very interpretable parameter. Rather than just tuning lambda, I'm saying, I'm going to try different values of K for the sort of low rankness, for the rank of the matrix. And when I put down like K equals 2, 3, 4, 5, 6, even when I'm misspecifying it and giving it more degrees of freedom than it needs, the projector is actually making it look even better. There's some noise when I'm way off, but for many such cases, it's pretty much recovering the truth exactly. So we see that it's pretty robust even to the tuning here. Right, so again, this is the same algorithm on 2 different problems so far, and despite the generality of this approach, it can be competitive with the leading techniques that are more sort of bespoke for each individual problem. So this next part of the talk, I want to focus on maybe a more challenging task, and this is sort of a classic task of covariance estimation. It's a little bit related to some of the things that we've heard earlier today too. And I'm actually really elated to see that one of the people who is very influential in this line of work, Jacob Dean, is in the audience today. I didn't realize he would join us. So I'll talk about how we built on that work from the perspective of MM. Let me motivate this problem because it's a little bit different than regression, but it's of course a very classic problem to estimate the covariance of data in statistics. And sort of our favorite way to do so is to take this simple sample covariance estimator. This is the maximum likelihood estimator if you correct for the right number of the right coefficient here. And of course, it's very well known since the 50s that this is going to do a very poor job in high dimensional settings. In fact, it's singular, so you kind of already know your shot. And again, very naturally, if you think that there is some lower dimensional structure in your high dimensional data, it's natural to try to look for a sparse solution. At least that's one of the most general ways to look for something well defined here. And it makes sense here just as anywhere else. But in this case, the computation is much more challenging. Okay. Let me motivate some of the prior work. There is thresholding directly on that sample covariance matrix, but I would argue that it's a nice, simple method, and I like simplicity, but it might be too simple in that there's no likelihood-driven part. We just have the sample covariance and then threshold it to make sure that it's more sparse. There's a lot of good work that assumes a little bit more structure on the type of sparsity we have. So you might think that there is some kind of factorization available for sigma, or if there's some banded or tapered structure. And this allows that sparsity to be much more tractable. You might have a decomposition-based approach, for instance. Well, a lot of these, well, of course, there's a particular type of structure, but also they might imply things like orderings on the variables, which might not be very natural. And then something that we've already seen, there's a much larger literature on estimating the inverse covariance or precision matrix. Okay, so or even a sparse version of this. We've seen graphical lasso, we've seen more recent developments. And in this case, it's a different problem. So they both are very important, of course. In fact, the precision matrix is looking at a sparse precision matrix, as we've seen earlier, encodes the conditional dependencies in the data. So this is really useful. If I have a 0 in the precision matrix in ij, I know that the ith variable is conditionally independent of the jth variable. And it might be that that's somehow more relevant notion of independence, but a sparse covariance matrix encodes something else. It means that if there's a 0 in the ijth entry, the variable I and variable j are marginally independent. So they're different, and you think that some people care about one versus the other, and yet the literature on precision estimation is way larger. And I think it's largely due to the fact that it's a nicer problem computationally. So the precision matrix is the natural parameter. To get into a little more details, it's convex in the precision parameter. And in the covariance cases, it's much harder, right? It's not convex. Nonetheless, the reason I love this paper, which was a little while ago now, they nonetheless tried to do sort of the hard problem, right? So this is one of the fewer in the smaller literature that actually tackled penalized estimation for a sparse covariance matrix, right? And I'm going to talk a little more about why this is hard. And using the likelihood, right? So here's the log likelihood of Gaussian data, and you can also maybe use this as a pseudo likelihood if you don't actually want to make the Gaussian assumption. And then estimating this sparse sigma then can be cast as a constrained problem under this set, right? So I drop the n over 2s for convenience. And then what I need is I want the thing to be sparse. So I'm making the, let's say, k free parameters. So because of the diagonal and the symmetry, I wrote 2k plus b. I want k free parameters in the covariance matrix, the rest being 0. And I also want this to be positive definite. All right, so this is what they considered. And like I said, this problem is difficult because that non-zero, sort of the sparsity set is difficult. We have an additional constraint. And then, you know, the natural thing to do, especially at that time, was to look for things analogous to lasso. In this case, we have an L1 norm on basically the covariance matrix. We can also have a Hadamard product with some adaptive weights in front of it to make it perform better. So again, the nice thing about precision matrix estimation, that's a convex problem. Doing graphical lasso, putting an L1 penalty preserves the convexity. In this case, you started with a problem that was non-convex. Now I add an L1 penalty, it's now non-convex and non-smooth. It's really hard. And so the way they did it, maybe unsurprisingly for this audience, is that they indeed were able to make a lot of progress on this challenging problem using MM. And we're going to revisit that using MM as well, sort of inspired by their sort of path-breaking approach, but we're going to replace that L1 penalty by that distance penalty I've been motivating in this talk. This is a harder problem also because the log likelihood itself, like I said, it's non-convex. It's not going to be an easy likelihood to begin with, like the GLMs. So in this case, we're not only going to substitute the distance penalty, but we're also going to make a majorization of the loss function. Right? So that takes a little bit more work. but it's not so bad. So what we want to do is we start, so remember F is the loss. We start by taking matrix derivatives. So, okay, matrix derivatives are not fun, but we take matrix derivatives and kind of get this quadratic form. And it's nice because, again, if I apply this Fisher scoring trick, trick related to Fisher scoring we like by replacing maybe things like sigma by its expectation, it simplifies greatly. And we see that this is a reasonably wieldy expression for that second differential. In particular, it's positive definite, just like we saw in the last example. And then together with the distance majorization, what I'm going to do is Taylor expand using these terms and then put in the penalty. So instead of just the loss of sigma, I have it anchored at our current iterate plus sort of the first and second differential terms and the distance penalty. Okay. So a lot of notation here, but really it's a second order, it's a quadratic expansion. So it's a quadratic surrogate function plus a penalty. Now, the nice thing, again, like when I have a sigma k under here, you can understand if I didn't apply this simple but useful trick of distance majorization, my optimization variable sigma would also be under this projection. So there's going to be no way I'm going to sort of take derivatives and solve for zero, set to zero and solve for sigma. But what the beautiful thing about these ideas and the way it plays with MM is I can actually rearrange this just using simple algebra and get a closed form for my solution. Right? So sigma here, I have to write it in a different form with vectors and Kronecker products, but it has a closed form solution. And in fact, we didn't stop there. Like there's so many great computational people in this audience, and sort of that line of thinking makes you think that even when you have an analytical solution, what if you can do better using computational tools? And a really neat thing in this research was that we found that instead of just directly using this neat solution, we can actually apply some nice algorithms that were pioneered in control theory for certain matrix equations. In this case, it was called the Sylvester equation, and actually reduce this by 3 orders of magnitude from, so because of the Kronecker product, this is power p to the 6 complexity. And using this kind of nice trick, which I'm not going to go into details about, reduces it to p to the 3rd. So the kind of computational thinking that I picked up a lot throughout this kind of work really makes this tractable for large data sets. Now, I haven't even talked about the other constraint, positive definiteness, right? And that can be a tricky one. It's a set with a lot of beautiful but complex geometry. And in this case, we wanted to make things as simple as possible. And so what we did is we have the projection with the distance penalties for the sparsity. But what we want to do here is just use a very simple approach, which is just backtracking to make sure we remain within the positive definite cone. Right? So if we can just have sort of an interior point thing going on, that would be even better. And indeed, because we have that nice positive definite form for the second differential, we know that we're always kind of pointing in the right direction. And if we can just prove something about backtracking, which we did, we can show that we can mostly worry about the other constraint with the projections and just backtrack sufficiently to make sure that we remain inside that feasible set. Okay, so the proposition here, I'm not sure why none of these rendered when I last compiled this, but we show that this works out for this problem. And not only that, empirically, we actually observed that this is rarely required. And I think that's just a testament to how well those surrogates are working in this case, those quadratic surrogates. Okay. So just to contrast again with sort of the work that inspired this, in the past work, we have the same likelihood-based perspective, but a different penalty. And again, they actually used MM to overcome the computational challenges here. And in particular, it's this concave-convex procedure by Yuil and Ranganan, I believe. That uses a linear majorizing function, which can be a little looser if it's a region of high curvature. And then the tricky thing is, again, there's 2 constraints. And so to enforce that positive definiteness, at least in this case, there's an inner subroutine that calls ADMM, which was sort of talked about today, to make sure that we're within the interior of the positive definite cone. And that can be a little bit slow to run when we have to call it. So in this case, because we went to the second derivative and showed that it's pointing the right way, we not only have sort of height approximations with fast updates, but we don't have to worry about sort of additional subroutines to enforce the second constraint. Right? And then we can get the explicit minimizers of each surrogate, which is really nice. In the first example I gave, we're actually taking Newton-like steps, so we're not getting right to the minimizer of each surrogate. I don't want to go too much into the theory here, but it was really interesting to find the convergence properties of this because, again, we have a non-convex constraint set, and usually when you have these things like projections, we don't even know whether they're single value. You have a non-convex constraint. But we were able to use some nice Zangwill convergence type theory on the algorithm map itself to show that it does converge to that all the limit points are stationary points of this objective. Okay, so not quite strong enough to prove that they're minimizers, but in practice, we observed that it's doing the right thing every time. So just as an example, we kind of revisited some classic simulation setups in terms of sort of random structure on the non-zeros, as well as sort of a clique structure on the covariance matrix. And in terms of entropy loss, which is a natural thing to look at for covariances, we do see that our method, which is the black dash line here, is performing well in the sense that we're evaluating all of the competitors on all the full range of possible non-zeros, and we're actually selecting sort of the right number of non-zeros in the simulated example, and obtaining low losses there. I'm going to skim over the simulation results again and then go over sort of a more telling case study. But the other thing here is we're comparing this now to those classical estimators based on threshold and sample covariance, as well as a related approach that also enforces a log barrier constraint by Rothman to enforce the positive definiteness. And what we see here, again, it's a table. I don't want to make you look at a table too much, but soft thresholding, kind of a lasso type approach, ends up giving a lot of spurious predictions, as you might expect. So a lot of false positives, although it doesn't really have any false negatives. Hard thresholding, on the other hand, tended to have more false negatives and only does just about as well in terms of false positives, but similar with the log barrier approach in soft thresholding. But our method is achieving a really nice balance of those two and kind of doing better overall. We have the same in terms of entropy loss. I'll skip over that. What was maybe more interesting is we revisited a very classic case study here. So it's definitely not sort of a cool modern big data setting, but it's very interpretable and sort of has been well studied. And I don't have enough text on this slide, but what we wanted to do was revisit sort of a flow cytometry data set from the original graphical lasso paper and revisited from this first sparse covariance paper by Bean and Tibshirani. So here we only have 11 variables and measured on a lot of cells for expression. But what we wanted to do was try to estimate this graph in terms of different sparsity levels using different algorithms. And let me just be careful here. So the middle here is the estimates using. So the middle here is the estimates using the graphical lasso. And so, or some kind of precision estimation, right? So here we're estimating the sparse precision matrix, and I'm plotting the non-zeros at fixed sparsity levels. So here I'm looking for 16, here I'm looking for 9. On the left, I'm applying the previous sparse covariance approach. So there's no reason these should actually match, because the middle one is estimating the sparse precision matrix. That's the non-zeros there. And the left is estimating the sparse covariance matrix. So this is the non-zeros in the marginal dependent structure. And they're quite different. So I'm looking for 16 edges and 9 edges, and I put down the edges, but they're in different locations. And a priori, there's no reason that that's a problem because they're different structures. However, the one on the right is our method, and we're estimating the same object as the method on the left. And so when we match the sparsity levels only, we found that they differ, but also these estimates of the sparse covariance are a lot closer to what the sparse precision looks like, right? Which is kind of telling because they're different objects, and so there's no reason that either one is wrong, that these aren't exactly the same. But you would think that maybe at some sparsity levels, there should be a lot of relationships between the sparse covariance and sparse precision. And without any side information, the fact that these are closer than this previous approach makes me think that, indeed, it could have been sort of spurious predictors selected on your L1 penalty, whereas our sort of more direct penalty on the sparsity is doing a better job, right? So the take home on this example is that maybe the marginal and conditional covariance structure in such applications might be more similar than we knew. And this is the kind of thing that we can learn about sort of with a little bit more confidence when we have better computational tools for these hard problems. Great. Okay, so I don't have much more time. I'm going to start wrapping up and just talk a little bit about future directions after giving a message on what we talked so far. So we've seen that distances of penalties in MM, at least in this narrow view so far, gives us a powerful framework in particular for this hard problem of covariance estimation without assuming any structure on the sparsity, right? So this is something that hasn't been done much. We have nice convergence guarantees. The penalty avoids that kind of unwanted shrinkage, which we've seen in multiple case studies, more in the paper, as well as simulations. And in this case, we have two constraints, but we can really gracefully handle one thanks to that positive definite quadratic form, and gracefully handle the other by projections in this penalty framework. So for the Bayesians in the audience, and because I'm at Duke now, and the data suggests that if you are a postdoc with Ken, you will likely get shipped off to North Carolina somewhere right after your stay. So we've had a lot of fun sort of looking for connections and extensions of these distance set penalties. And so one very natural approach is to think, well, indeed, we can have analogs for things like the lasso, the Laplace or exponential priors. And so in this case, why not do something similar with these constraints? So if I wanted to constrain some variables from a Bayesian perspective into some set C, I can have an indicator function that modifies the posterior, which is a product of the likelihood and the prior. So maybe think of the whole prior then as whatever I wanted it to be times this indicator. But when you have these non-smooth things, it can be a headache for Bayesian samplers, especially for nice things like Hamiltonian Monte Carlo, which Mark taught us about this morning. So instead, what if I could replace this? Well, first of all, I can just rewrite this as the distance because we know that that's equivalent to this being in the set. And then because I don't want to have that sharp constraint, maybe we can replace that by sort of the exponential of something that looks very familiar from the beginning of this talk, right? So this is a super simple observation. And again, the simplicity here is the point so that we can use this in a lot of nice algorithms that already exist, right? So we're replacing the sharp indicator by something smooth, but we still have all the nice interpretation of this distance here. There's a lot of prior work related to this. In 2020, one of my colleagues, David Dunson, and his collaborators, the first author is Leo Duan here, have a really nice idea that also considers relaxations of this set. Also, Aki Nishimura is on this paper. He came through UCLA as well. And in this case, they also have sort of an exponential of some kind of distance here. In their approach, they really were focused on, let's say you have a constraint that might be in a different dimension than the data, right? So your data might be in RD, your constraint might be S dimensional, it's a lower dimensional subspace. They would write that constraint algebraically in terms of a system of equations where these should be satisfied by equaling to 0, and then sort of look at the L1 norm of the total constraint violation. There's some subtleties here. It kind of requires you in some high level to go from your original parameter space to the constraint space, do some stuff here, and then map it back. And the mapping back and forth can entail some pretty difficult geometric measure theory that not all of us understand. Furthermore, you can see that when I try to put this into some kind of gradient-based sampler like HMC, without all the details here, I took a derivative of that posterior, and then part of it, the part that has to do with the constraint when you don't square it and when you have something like this, is just given by this expression. You can derive this for the gradient. But you kind of see a problem here because at the denominator, you have theta minus its projection. And so when you get close to the constraint, which you might want to do if you want to enforce the constraint, you're inevitably going to encounter numerical instability because this thing wants to blow up. So you kind of have a discontinuity here, and that's not good for these algorithms. And especially nowadays, a lot of people want to use sort of these nice implementations of the algorithms right out of the box. So when you want to do gradient-based samplers, like our observation here is so simple, it's just try the squared version, basically. But there's a couple things going on. I'm not going to motivate all of this because Mark did a great job doing it already. The idea here is that your log likelihood kind of plays the role of a potential in a physical system. So if your log likelihood is something you want to maximize, flip it upside down and think of your Markov chain as like a ball rolling around in that well. And so if I have that going on, those can be expressed by the Hamilton equations. And this is something that we're going to use to design a Markov chain Monte Carlo sampler. But the idea here is that we can see that all these derivative type things are going to be nice when we have a squared distance that has a nice closed form derivative expression without blowing up in the denominator. And because we're only going to evaluate projections of theta onto the constraint, it's a more subtle point, but sort of we're always staying in that original space. We're not actually going to the lower dimensional space if we have a lower dimensional constraint. We're just looking at how far that would have been violated, but all of that is kind of implicit under computing the projection, which again is a nice thing to compute. So I'm really just breezing through this work. There's a lot more. We have some theory, it's recent work, but just as one simple example, if I pretended I didn't have a nice R package to sample from a particular manifold constraint, the von Mises-Fisher distribution on the surface of a sphere, I could try to use one of these generic constraint relaxations and try to use HMC. And when I used the previous approach on a slightly more difficult problem, but the same class of problems in the original paper, I would say that this posterior looks nothing like the theoretical draws from that distribution, where under our distances set prior, maybe it's not as fleshed out because there's some correlation, but we do see that it's sampling, at least visually, from the right distribution. And we have some theory to back that up too, that I won't talk about today. So let me just kind of conclude with some thoughts. Right, so so far has allowed us in all of these examples to elicit simple but effective algorithms for a broad range of problems, mostly from that optimization perspective, but very recently very interested in sort of these Bayesian connections. I should also say that in the audience here, both Eric Hua and sort of a recent graduate, star student Shrinkage from UCLA, have been working on more general sort of proximal priors that are just really beautiful work kind of in this direction. So I have the same problem. If I look up Hua on Google Scholar, all my ideas are already there. So I won't even bother to look up Ginevra if I want to get to sleep at night. So in this case, we're originally doing optimization, but now we're really interested from a Bayesian lens. It comes with sort of free uncertainty quantification in the posterior, because deriving things like confidence intervals is such a difficult problem when you want to deal in the generality of set-based constraints. Right? We're doing some more work on sort of justifying heuristics for increasing that penalty parameter rho, local majorization, more non-convex analysis, and just trying to build up a suite of projection operators. And thankfully, there are a lot of strong research groups building toward the same objectives. Also, I'm recently interested in kind of applying this. We've put this sort of on the input in a prior in a model, but these smooth penalties play really well with neural networks too. If you can have a smooth output layer constraint, to constrain the outputs of something like a deep neural network, you can backpropagate that all the way with some very nice computational tools that Johan, for instance, overviewed to get all of the machinery working really nicely, right? So the smoothness is really great. And I would say there's still plenty of open directions, not only what I just kind of overviewed briefly, but the statistical theory really is wide open. And one thing I'm really excited about from the Bayesian perspective, for the Bayesians out there, you kind of know there's this landmark paper by Ismael Castillo on sort of why the Bayesian lasso or Laplace prior is actually not doing well in terms of posterior concentration. Right? We usually have asymptotics just being the way we can say nice things. But in that case, maybe unsurprisingly, that is just something that's sort of focused around zero. So if we were to let things go to infinity, it ends up collapsing to something kind of degenerate around zero, because zero is not the same thing as the sparsity set. In some sense, these kinds of priors give us more hope in maybe deriving more favorable properties, because it's not just sort of a beautiful mathematical coincidence that the boundary of something like the L1 ball induces sparsity. It's that we are working with the sparsity set with a full interior that makes sense. So just to start some more high-level thoughts, I think that hopefully you see, maybe I talk too much and have too many things on my slides compared to Ken's beautiful and elegant presentations, but what I've sort of realized on working on this line of work with Ken is that simplicity really is the point. And just some more sort of navel gazing here, I think of as, again, it's more of, it's not just one algorithm, it's sort of an art in designing things that kind of balance the complexity of what you want to do. And there's, you know, for those of you who kind of read about public intellectuals and things, so the late great thinker, Edward Said, was always obsessed with this idea of sort of an artist's late style, okay? And so he was really thinking that, you know, to understand Shakespeare, you read The Tempest, you listen to the Ninth Symphony or the last 5 sonatas of Beethoven, and you see that that really is sort of the culmination of them at their artistic powers, and like really understands their whole life's work. And you know, this is also why you watch Lionel Messi on the field, and you know, he looks like he's not moving around a lot, but really you realize he's actually playing a very beautiful game, and he's at sort of the height of his powers. So I put in Messi there to make sure I'm not just calling you old, Ken, so you're welcome. But the idea is, I do think that in working with Ken during my postdoc, you know, he totally derailed what I wanted to do, but I was really benefiting from his understanding after a career of contributions all over the place. This is actually one of at least 2 Lange Symposiums I know about. This is the better one, but he's outside of all the things we've seen today, he's also made amazing contributions to genomics and everything. And so I think what I got to understand here is that, you know, Ken has written the book on many topics on optimization and applied probability, and he was obsessed with So I can only trust that, you know, this really is some kind of unifying, beautiful perspective. And as I work more and push forward on all these directions, I'm really seeing it everywhere. I'm really slowly understanding that. So I do want to say, not only have I benefited from sort of all of this great wisdom and all of this great work that was put before me, but also during my postdoc working on this, it was such a great time of my life. Ken is not only an excellent mentor, but a rare friend. So I'm really glad to have benefited not only from all of the guidance and from this community, but from sharing a rare friendship. So thank you all, and I'll leave you with some references. Any questions?
More of a clarity if you could provide it. It all seems too good to be true in the sense that it seems so easy. I mean, maybe it's just your style that you made it seem so easy. For those of wishing to get into this, what would be the traps we would fall into if we start thinking these for developing novel algorithms for
Yeah, it's a great question. I mean, we've certainly encountered difficulties too, right? So I think the framework is really elegant. The things that you have to keep in mind is it's not always easy for anything you want to do to compute those projections, right? So you kind of need to pick the right problems. It's also not always easy to derive these majorizers for any kind of loss. It's not like EM where you know that you're at least trying to derive an expectation. You're trying to look through all of Ken's book, like looking for different tricks to do on the particular geometry of that problem. The other thing is, just because the tuning here is sort of more satisfying in the sense that it's not like lasso where you need to hit the sweet spot, you know that you're obeying the constraint in one direction. There still is an amount of engineering in choosing that penalty parameter, because if you make it closer to the constraint, you're also more driven by the constraint than your data fit. And algorithmically, that translates to maybe sometimes a smaller step size driven by the likelihood term. So there are trade-offs all the time, and there's some tweaking to get it to work really well. But when it works well, it works really well. So, yeah, good question. Yeah. Okay, yeah. Here, right? A different one. Oh, yeah. Sure.
Okay, you'll see that sample covariance matrix is not singular
Oh, yeah. It's a great question. So here too, we do talk about that in the proof of this. So basically the covariance matrix itself is already going to be non-singular. So it's sort of in all of these papers we've read, you either do something like, it's similar when you don't need an assumption on the covariance matrix. The assumption we've seen in the past is to assume that you're not just in the positive definite cone, you're in something where the smallest eigenvalue is separated by a small number. And that's actually, so that smaller space is actually a strictly stronger assumption than if I were to take the non-singular covariance and add some tiny multiple identity, which is what we recommend. So the theorem, we write this and then we say, well, how do we satisfy that assumption? It's simply you would have sample covariance plus like tiny delta times identity. And that's a little better than saying the whole space you're operating in is sigma is not just greater than or equal to 0, but greater than or equal to delta times identity. Okay, so it's still not perfect, but that's how we, in practice, it's actually really simple because you can always do that. Yeah, thank you. Yeah. Oh, sorry, I didn't. Somebody back here?
You wrote the paper.
Yeah, there you go. Oh.
That was a great talk. Yeah,
thank you.
I just like, yeah, the choice of that. I don't see like if you're, for example, the covariance problem, you can make, you have the choice of K, which is how Sparse is, and then the choice of row, I guess, is how close you are to that K Sparse.
Exactly.
So, do you have a way to say how close you are, like for a given choice of row, how close you are to a K Sparse solution, or is there? Because you can imagine like a bounded version of that maybe you could say like if I want to be very close to a K Sparse.
Yeah.
So then if I do something.
So it's a great question. I haven't thought about that too much. I guess the question is like, so in this case, you have a parameter K in here, and that's explicit in terms of the sparsity level. But now you have a parameter rho, which is somehow related to how close you are. And so is that explicit? So in some, like in our Bayesian work, we found a connection to exponential tilting. And so you can now quantify a constraint in terms of the expectation, like a KL difference. And if that's sort of a concrete number, you can then figure out what row corresponds to that. But in this case, we simply say, well, if you really want it to be close, you want row to be large. And like I said, in balancing these things, so far, we kind of use an increasing row schedule throughout the iterative algorithm. And then finally, if let's say you now want the output to be something that is very much a covariance matrix, so you need the constraint to be satisfied. Sometimes, when we have a increasing schedule and it kind of wants to converge empirically and just numerically it says it's done, you can just follow it up by doing one step of projection on the output of your algorithm. And so then now you know that the answer to that is 0, right? It's perfectly obeying the constraint. Yeah, great question. Mm-hmm. Yeah.
I'm fascinated by your point about the covariance and precision actually having the same sparsity structure. And there's this really nice paper from the 1990s that basically says that if you're looking at positive depth matrices, then as you increase the sparsity, that in general, the set of matrices that satisfy this sparsity becomes smaller and smaller. That is the set that is sparse, but has a sparse inverse. And eventually, as you increase the sparsity enough,
They're no longer. Interesting. Interesting. Huh.
So my question is there some sort of middle ground, some sort of level of sparsity where we can have interpretability for both the precision and the covariance?
I mean, it's a little beyond my career grade. I didn't know about that paper. That's awesome. And it makes sense. I think, in this example is P equals 11. I think as you get larger and larger, they should agree less and less, you would think, but there's still some set that, of things that they would agree. As far as interpreting those, the ones that share that structure, it just must be something where it's just the dependence, the signal is extremely strong, right? Because it's agreeing from both views. And like I said, they are kind of agreeing empirically in my example, but I'm not claiming they should be the same, right? So I don't even know if that example, the truth is in that set. But if you had such a strong, I don't know if people kind of study that specifically, like what are the implications of having shared conditional and marginal dependent structure, but that sounds like something really interesting to look into.
Like a block diagonal matrix.
Yeah. Mm-hmm. Interesting. Yeah, I'll have to think about it. Okay.
It's sort of a general are there any methods for point estimation of variance that differs from variance strategies where say you want like a sparse inverse covariance, but you want a compatible covariance matrix?
I'm not sure. I mean, again, that can be a pretty difficult constraint, though, I would say, right? Because like we were just saying, you don't know when that's both achievable simultaneously. So I guess naively putting that constraint in and something like this, you can at least find a compromise. But I just don't know how to interpret that compromise personally, but that's also really interesting. Yeah. I will say this is my first foray into really covariance estimation land, so I'm not quite an expert. Yeah. All right. Thank you.